Hello. With this session, we're going to begin the first half of this course, which covers the first and basic part of symbolic logic, formal logic. If logic is the science of truth, actually, you might also call it the algebra of truth, then we ought to start with the most basic things that can be true, namely, as you might want to call them, sentences, statements, assertions, or propositions. Philosophers can use those terms, statements, etc., in different ways to emphasize different features of them, sometimes to pick out different entities. For our purposes in this course, I will be using them interchangeably. Now, the kind of logic that uses these true and false sentences or propositions is therefore known as sentential or propositional logic, also known as truth functional logic. Already, even in saying that a sentence or a statement is something that can be true or false, I think I'm demonstrating the first point at which logic begins to depart from the language it does such a good job of illustrating and clarifying. Because in the perfectly ordinary sense of the word sentence, there are many sentences that are neither true or false. Look out behind you. That's an imperative. Where's my phone? A question. Oh, that this too solid flesh would melt, thaw, and resolve itself into a dew, the expression of a wish. Those sentences, and it's perfectly okay to call them sentences, but they do not have a truth value. They are not true and false, right? We're only concerned in truth functional logic with the kinds of grammatical sentences that have a truth value. And truth value just means one of the two values, true or false. Sometimes people will look at the symbolism in logic and they'll say, it looks like algebra or something like that. Well, if it is algebra, then you might think of it as an algebra that has only two numbers in it, the number true and the number false. Once in a while, and this is an old-fashioned thing, but sometimes people used to use the notation 1 for true and 0 for false. We're not going to do that, but it has the advantage of illustrating how logic can be like an algebra of the true and the false. When we're speaking of propositions in general terms, we will symbolize them with single letters, lowercase letters, and famously, symbolically, P and Q. This is like the X and Y of algebra. The P and the Q do not represent any particular sentences. Like if there was a sentence, this is logic class, and maybe we might symbolize that with a lowercase l and say, let L mean this is logic class. When we're talking about sentences in general, things that operate as they do simply because they're sentences, even when we don't know what their sentence is about, then we use P and Q. Now take one of these propositions, P. Because the algebra of logic only has those two numbers in it, true and false, we can describe all the possibilities for P and Q in a way that we cannot do for X, Y, and Z in algebra. We can say that P, for example, we're dealing with P now, we can say that it's true, or we can say that it's false. We name those truth values T and F, right? So T and F are the two possible truth values for a given proposition, P. And already now, having covered P and Q and the truth values T and F, we're in a position to learn the first most basic operation we can perform on propositions in our propositional logic, and that is the operation called negation. Negation You've got P, and you've got the negation of P. Depending on what your computer permits, depending on what your aesthetic permits, you can mark just a simple dash for an M dash for the negation. You can make it tilde. You can get kind of fancy. In each case, some horizontal line of this kind before the P tells you that when you are asserting P, you are now asserting the negation, not P. It's not the case that P is not true. And as long as we're just in the kind of logic that has these two truth values, true and false, we can define negation by saying whatever truth value a proposition has. Negation gives it the other truth value. Now, we can say this in a loose way, you know, if P is true, the negation of P is false. If P is false, the negation of P is true. But thanks to the CUNY system of colleges and universities, human beings possess a way of defining a connective like negation with utter clarity and in a standard universal form. This works for negation. We're going to use a similar method of definition for conjunction, disjunction, and other connectives later in this session. But let me just start with negation. We're going to set up a truth table that has P on one side, and we're going to define not P in terms of P. All right. What are the two possibilities for P? It can be either true or false. If P is true, not P is false. If P is false, not P is true. Those are all the possibilities for negation. We have now given a precise, thorough, exhaustive definition of that connective called negation. Why did I say thanks to CUNY? Well, CUNY, as you know, as a university, has been around not that long, since since my childhood. But some of the older colleges at CUNY have been around since the 19th century, like City College, the City College of New York, originally a standalone institution, now part of CUNY. Back in the early 20th century, a young man went to City College. His name was Emil Post. Post was an undergraduate at City College, then completed his PhD in mathematics at Columbia University. He wrote his dissertation 100 years ago in 1920. He published the essential parts of it in a paper the following year, 1921. So in this academic year, we are celebrating the centennial of Post's dissertation and his publication. And then after becoming a PhD in mathematics, Emil Post went on to teach at City College. So we can honor him as both an undergraduate of CUNY and as a CUNY professor. And I say this because it was Emil Post who really developed the systematic use of truth tables to define and to explore the meaning and limits of connectives, all right? No other institutions that can say that about truth tables, that the truth tables are the product of their institution. All right, that's a little cheerleading for CUNY. A truth table displays all the possible truth values for a proposition or for a set of propositions. And it is used, as here, in the first place to define logical connectives, right? And as you can imagine, all that the negation does is to not just put a not somewhere in the sentence, but to put a not in the sentence so that the sentence means the opposite in terms of its truth value of what it had meant. If the sentence is, I have 2 kidneys, the negation of it says, I do not have 2 kidneys, or it is not the case that I have 2 kidneys, or it is false that I have 2 kidneys. Negation is the only connective that operates on a single proposition at a time. The standard connectives we're looking at operate on two, and then they can be grouped together and nested to operate on more than two at a time. One of the fundamental connectives is conjunction, represented by and. And so if we've got the proposition P, the proposition Q, we can write P and Q with the ampersand. Some people like the upside down V, P and Q. Some people like the raised period or dot. Okay. I've seen every textbook has its own preference. It's a simple operation that applies to two propositions. It is sunny and the little birds are singing. I am happy and healthy. Well, I am happy and healthy. Be careful with something like that. Yes, it's a conjunction, but we would need to replace it with a more explicit statement before we could see the exact conjunction at work in the sentence. Because we don't want to divide it into the proposition, I am happy, and then the proposition, healthy. We want to write it in its explicit form, I am happy and I am healthy, and then you can see the and divides it into two complete propositions. Of course, one can connect more than two sentences at a time with and. It was raining, and soon the windows were wet and you could not see out. But for now, we're going to concentrate on a single pair of sentences joined by and. As we could do with negation, so too can we, with conjunction, use a truth table to define the operation. The difference is that you can't have a conjunction unless you've got two propositions that you're conjoining. So we need a larger truth table. We're going to start with a truth table containing two propositions, again, P and Q, and we want to spell out all the possible truth values that those two propositions are going to have. Now let me begin by showing you what we do when we set up a truth table. If you've got two propositions, you're going to have a truth table with 4 rows. If you've got 3 propositions, you're going to have a truth table with 8 rows. Yes, if you have n propositions that you're looking at, the truth table will have 2 to the nth power rows. And the standard way that you map out all the possible truth values is you have the first half of the rows be true in the first column, the second half be false, and then within that truth, you have in the next column, the first half true, the second half false. You want the last column, in any case, to be the alternation between T and F. And these are the truth values when we define conjunction. The conjunction P and Q is true when P is Q and Q is true. And in every other combination, it is false. Now let me add one qualifier. And again, the theme today is, the theme all semester is, there are going to be some departures from grammatical form as we enter logical form. logical form is always supposed to be exhaustively and clearly defined so that there can be no ambiguity about what P and Q means. There are additional meanings that sometimes enter into an English sentence that uses and, that we simply can't find room for in logic. So for example, if you say, she bit into the apple and fell asleep. Okay, notice that's very different from saying she fell asleep and bit into the apple. That kind of and, that's a narrative and, is non-commutative, but the and of logic is commutative, by which I mean if you put Q and P in the third column, the truth values are exactly the same. P and Q means the same thing, is true on the same occasions as Q and P. Nor does the logical connective, as it doesn't have a temporal sense, meaning that one thing happened before another, nor does it imply a causal connection, as we get, for instance, in the sentence, at the start of winter came the permanent rain, and with the rain came cholera, right? That implies the rain comes, and because the rain comes, the cholera comes. We're not including any of that causal meaning in our logical and. Also look out sometimes for things that look as though they're going to be logical connectives but are not. Fred and Ginger danced. Well, you might say that's just the same thing as asserting Fred danced and Ginger danced, but no, 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 for the beautiful thing is that they danced together. Okay. All of those connotations, I'm sorry to say, have to be left out when we translate natural language into logical language. We gain clarity, we lose nuance. Now, if in one sense the conjunction leaves out some kind of ordinary and sentences, some kind of ordinary and conjunctions, there's another respect in which the and of logic can include things that don't look like ands in natural language. Sometimes we conjoin sentences with a semicolon, for example. That's just the same thing as conjoining them with an and. When going to sleep, he locks his doors. When even in his house, he locks his chest. Two sentences, they're asserted as both true. That's a conjunction. No word and there, but it doesn't matter. The semicolon conveys the same logical meaning as the word and. In a natural language, in English, we can use but and although for the same logical effect. For example, when we say, they suspect that power is being drained off, but they don't know where. Or, it is sometimes advantageous to be unseen, although it is most often rather wearing on the nerves. Now, in both of those sentences, the but and the although assert that both of these individual propositions are true. They're both being asserted. It's true that in natural language, the words but and although connote something else. The sense that now we're hearing something different. We're considering another possibility. Those overtones to the conjunctions but and although do not remain when we translate them into logic as conjunction. But what we're translating over into logic is this sense that two propositions are being asserted and the result, the conjoined larger sentence, is true if and only if both of the element propositions are true. When you look at the definition of conjunction on a truth table, as you see it on the board right there, maybe your first thought is, wow, sure is hard to make a conjunction true. Everything has to fall right into place. You need P and Q both to be true, and in every other combination, the result, P and Q, is false. There's a complement, the complementary, simple, elementary conjunction to connective to conjunction is disjunction, which is, you might say, as easy to make true as conjunction is to make false. Okay. Disjunction is or. Again, there's more than one way we can write the or, but most commonly people use something that looks like a V, P or Q. And as we could with conjunction, as we could with negation, as we can with every logical connective there is, we can define disjunction in utter clarity with a truth table, thanks to Emil Post. As I said, disjunction is just as easy to make true as conjunction is to make false. By that I mean the following. The disjunction P or Q is true just in case either one or both of the elementary propositions is true. If P is true, the whole thing is true. If Q is true, the whole thing is true. If they're both true, the whole thing is true. The disjunction is only false in the one situation when P and Q are both false. Now, right, so trees are deciduous or they are coniferous. Okay, that's true as long as trees are either coniferous or deciduous. Tomorrow it will be cold or a high wind will blow. If it's cold tomorrow, that's true. If a high wind blows tomorrow, still true. If it's cold tomorrow and a high wind is blowing, it's still true. The disjunction allows for the truth of both propositions. In this respect, the or of logic departs a little bit. Again, a departure from grammatical form to logical form. The or of logic departs a little bit from the or of English, for example, because the or of English can sometimes be used in an exclusionary sense. It's the exclusionary or. Tomorrow we can go to the zoo or we can have ice cream. Of course, your reply to that statement is zoo and ice cream, but it's clear that you're being told it's one or the other, not both. You're not going to have ice cream and the trip to the zoo tomorrow, so you choose. That's the exclusive or. The or of disjunction is the inclusive or. It's not really what we express in English with the emphatic either or. There is this thing that some people say in English. I don't like to use it. Let's just say it this one time. We won't talk this way in front of little kids, but sometimes people say and or. You know, that's to capture the idea of an inclusive or. I mean, it's not English. Is it and or is it and or? Nevertheless, the nice thing about and or, the only thing I'll say in its favor, is that it captures the meaning of the logical disjunction. You might have P, you might have Q, you could have P and Q, either way. Now, again, because the disjunction is an inclusive or, the order does not matter. That's what we mean when we say a connective is commutative, just like addition is commutative, right? And subtraction is not. 7 plus 3 means the same thing as 3 plus 7. 7 minus 3 does not mean the same thing as 3 minus 7. But 7 plus 3 means 3 plus 7. P and Q means the same thing as Q and P. P or Q means the same thing as Q or P. They're both defined the same way. If one or the other or both are true, the whole thing is true. There's another kind of parallel between conjunction and disjunction. Just as the English but and although turn out to have the same logical function as the logical conjunction and, so too there are words in English that don't look like or, but they turn out to mean the same thing as or. Some of this we're going to come back to in a later session. I want to cover more ground today, and then I hope we can return and do a little review. But one example of an English word that does not look like or, but carries the same meaning as or, is unless. Unless suggests something very different. However, when you look at how unless works logically, I will die unless I drink some water, you are asserting I will either drink water or I will die. Melanchthon never wandered unless she was with Jeff Campbell means Melanchthon never wandered, or else you can bet she was with Jeff Campbell. Now, does the word unless really imply, connote, suggest everything that the word or does? Preposterous, right? And we're not asserting such a thing. Again, when we let a conjunction enter into logic, when we translate into logic, and this is different from translating between any two natural languages, we assume that we're going to leave all the overtones of the meaning behind, overtones of the word behind, okay? And we're going to preserve only what there is in the word that can be captured in, defined in a truth table. Okay. So far, we've looked at negation, conjunction, and disjunction. Today's session has one more connective, the material conditional. And this one, I'm afraid, is the only one that's a little bit tricky. When we have these two propositions, P and Q, we can connect them with, sometimes people use this horseshoe shape, sometimes an arrow, to mean if P, then Q. All right? Or sometimes people like to say P horseshoe Q. We do not say, although sometimes in a misleading way, in a casual way, however, in an incorrect way, someone will look at the symbol and say, P implies Q. This does not assert that P implies Q. It's a material conditional. Okay. We're saving the word implies for a different logical relation, and that's going to come up later. Okay. Here we're just asserting the material conditional between two facts or states of affairs. If P is true, then Q is true. Here are some examples of conditional statements. If this is logic class, today is Thursday. If you like peanut butter, you'll love Peter Pan. If ifs and buts were candy and nuts, we'd all have a very Merry Christmas. Well, I'm not sure what that last one means, but I do know this. A conditional statement connects the truth of the second part to the truth of the first part. The first part, what we say right after the if P, that's called the antecedent of the conditional statement. While the second proposition, if P then Q, is called the consequent, the antecedent and the consequent. And look, we're already talking about the order in which things get asserted, and that already is something we did not find with conjunction and disjunction, all right, because conjunction and disjunction were commutative. You could assert them in either order. The material conditional is not commutative. If P then Q is different from if Q then P. The conditional sentence that puts the antecedent and the consequent together tells you that the antecedent's truth will make the consequent true as well. If you swallow that watermelon seed, a watermelon plant will grow in your stomach. If you put your fork in the electrical outlet, you'll get a shock. How do we define a conditional statement like this using a truth table? The truth table definition of a material conditional, I promised it was going to be a little tricky, but it's not tricky when the antecedent is true. So in this truth table, the first two lines of the truth table, P is true, right? When P is true, it's very straightforward to define the conditional statement. No one raises an eyebrow. There's no problem with it. What do we say? If P is Q and if P is true and Q is true, then if P, then Q must be true. If you put your fork in the electrical outlet, you'll get a shock. You put your fork in the electrical outlet, you get a shock. True, true. Suppose the antecedent is true, however, and the consequent turns out to be false. Well, then it seems quite natural to say that the entire material conditional, the conditional statement asserted, is not true. You swallow that watermelon seed, and a watermelon plant does not, in fact, grow in your stomach, right? The Q there turns out to be false. No watermelon plant in your stomach. What do we say? We say that that warning conditional, if you swallow it, you'll grow a watermelon plant in your stomach, that conditional was false. So with a true antecedent and a false consequent, we have the result of false conditional statement. There's no problem there. Now, normally, when we assert a conditional statement, it only matters if the antecedent turns out to be true. For suppose I say, if it's sunny tomorrow, we'll have class outside. Tomorrow comes and it's raining. Did the conditional turn out to be true or false? Well, it's irrelevant. The fundamental requirement did not come to pass, so it's as if the conditional had never been asserted. And really, if you wanted to capture the idea of if-then that we use, that we're comfortable with in natural language, we would be finished here. We'd say, well, this is what really happens when we utter a conditional statement in a natural language. If it's true, then true, then it's true. If it's true, then false, it's false. And if P is false, if the antecedent is false, it's as if the thing had never been asserted. We forget about it. Nothing more needs to be said. But again, we cannot define connectives that way in logic. Logic doesn't work that way. We have to have a meaning here, not regardless of what it is. That's a bad way to say it. But we have to have something either true or false, right? It has to have a value. How do we decide what to do when the antecedent is false? Well, let's try the fourth row of the truth table first. Suppose you've got a false antecedent followed by a false consequent. If false, then false. Maybe you can see why it's more natural to call that true than to call it anything else. To see why, think of a very particular type of conditional, one that we can symbolize, oh, sorry, just ruined the example. If P, then P, or if Q, then Q. Think of a conditional in which the antecedent is the same as the consequent. If you're happy, you're happy. If I'm right, I'm right. If we lose money on the deal, we lose money on the deal. Okay. Those are vacuous statements. If I'm happy, I'm happy. If it's raining, it's raining. They're vacuous in that, of course, if it's raining, it's raining. If I'm happy, I'm happy. But notice that the obvious truth of those assertions, they're after all platitudes, tautologies. Their obvious truth does not depend on whether the proposition being asserted is true or false, right? Take the example, if I'm right, I'm right. Okay, you have to agree with that. You gotta agree that if I'm right, I'm right. Okay, now, suppose I'm right. Then you have a true antecedent followed by a true consequent, no problem. Suppose I'm not right, okay? Now you have a false antecedent followed by a false consequent, and yet that if P, then P, that tautology, that pleonasm, that truism is just as true, trivially true, as it had been when P was true. Okay, so to capture this intuition, this, I think, very direct, very obvious intuition that if P, then P must always be true, we want the conditional to come out true when the antecedent and the consequent are both themselves false. So that's really not that difficult. That leaves us with only one tricky example to look at, in which P is false, the consequent Q is true, and we assert, for this is what we do assert in logic, that the resulting conditional statement is true. People sometimes find this unsatisfying. Again, we're not capturing everything that we normally say with if and then in ordinary English in a conditional. We have to give it some meaning. Why do we give it this meaning? Now notice, it's pretty easy to make a conditional come out true here. Just as easy as it was for a disjunction, in that 3 out of the 4 possibilities are true, only 1 possibility is false. It's just the false is in a different place from where it was in the disjunction, so it's not the same as a disjunction. Why this arrangement? Well, let me start with a couple of technical reasons and then give some more ordinary examples. Here's the motivating idea behind making the material conditional true when the antecedent is false and the consequent is true. We have one main task for the material conditional to perform. There's one thing it has to tell you, and that is that you do not want the situation in which a true antecedent is followed by a false consequent. That's what you do not want from a material conditional. A material conditional offers you the promise that you will not have that combination, right? The combination of true followed by false. None of the other combinations matters. So in that sense, you want to define the material conditional in the weakest way possible. Let it come out true whenever possible, as long as it doesn't come out true in that one situation wherein the antecedent is true and the consequent is false. Now let me offer a second semi-technical justification. If you don't like having this statement come out true, suppose you made it false. All right. Okay. Notice one thing. If the if then were false in that situation, okay, so that if P then Q would be true just when P and Q are both true or both false, then this would define if P then Q, and it would also define if Q then P. That is, the conditional would be commutative. And this indeed is the definition of a more complex connective we're going to get to later on, the if and only if. P if and only if Q. But that's a different assertion from if P then Q, right? Suppose our propositions are car runs, that's our P. There is gas in the tank, that's Q. If the car runs, there's gas in the tank. Please no counterexamples about electrical cars. Let's just live in the past for a second. If the car runs, there's gas in the tank. That's true. If you know anything about cars powered by fossil fuels, you know that that's true. Of course, you're not going to assert the opposite. If there's gas in the tank, the car runs. Hardly. All sorts of other things have to be true. The gas in the tank is far from enough to ensure that the car will run. Cars break all sorts of ways. Let's not even get into it. But you do know that if the car runs, there's gas in the tank. You just don't know that if there's gas in the tank, the car runs. Okay, so therefore the assertion, if the car runs, there's gas in the tank, is a very different assertion from the car runs if and only if there's gas in the tank. You do not want to identify the conditional with what we call the biconditional, P if and only if Q, right? That's the commutative. So in order to maintain the difference, the distinction between if P then Q and P if and only if Q, you have to define if P then Q in this different, what we call this weaker way, this way in which it's easier to make if P then Q come out true. Now, in talking about that last example, I did use the phrase only if. Let me round out this first session by talking about only if, how it resembles if, and how it differs from if. The logical formula, P horseshoe Q, can be read in a natural language in either of the two following ways with equivalent truth. If P, then Q, or P only if Q. Yes, these are the same assertion. If P, then Q, but P only if Q. Not as strange as it might seem at first. Only if identifies a necessary condition for something else to be the case. If identifies a sufficient condition. If the car runs, there's gas in the tank. So the running of the car suffices to tell you there's gas in the tank. It's a sufficient condition. If the car runs, there's gas in the tank. But we can also say the car runs only if there's gas in the tank. The gas in the tank is a necessary condition for the car to run. It's not sufficient. We've all been in this situation where cars have plenty of gas in the tank and yet do not run, but it's necessary, right? So if the car runs, there's gas in the tank. The car runs only if there's gas in the tank. So if P, then Q, P only if Q. And then the expression P if and only if Q, the biconditional, right? Which says if you've got one, you've got the other one. If you've got the other one, you've got the one. That can be written as a conjunction of two material conditional statements. For you see, and this will be the first example of that phenomena, for you see, we can build larger and more complex logical statements out of the simpler connectives. In this case, we would write if P then Q, and if Q then P. If P then Q, and if Q then P, so P if and only if Q, That one is commutative, Q if and only if P. Okay, thank you so much. That should be enough for our first session of connectives. It's elementary, but you don't want to have any confusion here. And you also want to get accustomed to the ways, and let me just repeat them for a second, the ways in which logic, in the interests of clarity and precision, compels us to drift away from the grammatical form and the semantic senses of ordinary language. Okay. We probably don't see it anywhere more dramatically in today's session than in the if-then. When, as I said, ordinarily, when you make an if-then assertion and the antecedent proves to have been false, it's as if the thing were never said. We don't have to have a truth value for it. In logic, we do. Logic form achieves a great deal, but it achieves it by moving away from grammatical form. Thank you.